Which species are likely to go extinct? We can get some insights by looking at the species that have gone extinct in the past. And to discuss this issue, I'm here with Daniel Field. So Daniel, tell me why have you brought me here?
Well, hi Bill. We're here in the Sedgwick Museum of Earth Sciences within the Department of Geology here at Cambridge. And we're here because this wonderful museum is full of brilliant fossils that document the history of life. And fossils provide us with the only direct evidence we'll ever have to understand how things like extinctions took place in the distant past. And so to help illustrate that, we've got arguably the most iconic fossil organism in the entire world here. This, of course, being Tyrannosaurus rex, a giant predatory dinosaur from the end of the Cretaceous period, and indeed the very end of the age of dinosaurs. T-Rex went extinct 66.02 million years ago, and it went extinct during a very important event in the history of our planet. That being the end Cretaceous mass extinction event, when a giant asteroid slammed into the Earth and caused the widespread extinction of groups of organisms all around the world. And that, of course, included all of the giant dinosaurs. Now, it's very common to say that all dinosaurs went extinct in the end Cretaceous mass extinction event, but of course that's not totally true, because birds, which of course themselves are dinosaurs, made it through that mass extinction event and of course subsequently did pretty well, diversifying into all of the living forms of birds that we have today. But the important principle illustrated by the end Cretaceous mass extinction event is that large-bodied organisms like T-Rex and all other non-avian dinosaurs, they're very large-bodied organisms. And that extinction event was highly size selective. So large-bodied organisms went extinct, and small-bodied organisms did comparatively okay. But this size selectivity was extremely severe. In fact, in terrestrial ecosystems anywhere on Earth, it doesn't seem like anything larger than about 5 kilograms, basically a house cat, survived. And so size selective extinction, both in terrestrial ecosystems and in the oceans, was incredibly severe. And there are very straightforward explanations for that. Of course, large-bodied organisms need to eat more than small-bodied organisms do. So when the going gets really tough, small-bodied organisms tend to do better than large-bodied organisms do. And the generality of that sort of observation in the fossil record has given rise to a term. We call it the Lilliput Effect. This tendency for lineages that make it through mass extinction events to be relatively small compared to those organisms that go extinct when the going gets really tough.
And of course, there have been a number of extinction events, we're illustrated in this museum, and I gather for each of the 5 big extinction events, the same Lilliput effect has happened. And you can examples of the large species have disappeared and the small species have persisted.
That's right. So to varying extents over the history of life, when we have these extinction events, very often it tends to be these large-bodied organisms that suffer disproportionately. And interestingly, body size correlates with a bunch of important biological parameters that also help to explain the generality of this phenomenon. For instance, small-bodied organisms tend to reproduce more quickly than large-bodied organisms do. They tend to have larger population sizes in general. And those sorts of factors, which scale negatively with body size, are the sorts of factors that increase the likelihood that small-bodied organisms will make it through relative to large-bodied organisms that are at more severe risk for extinction.
And this same phenomena occurs for other more recent species, doesn't it?
It's true. It's a phenomenon that is holding true in the present day. And looking at the fossil record of much more recent organisms, it's something that we can continually observe throughout the history of life. So one of the great things about the Sedgwick Museum here, which is one of the oldest earth sciences museums in the entire world, is that it's absolutely full of fossils of different ages that illustrate these principles really nicely. So over here, we're looking at much more recent fossils. These are fossils from about 10,000 years ago. And we're looking at another iconic extinct species, this one known as the Irish elk, which is an absolutely gigantic species of deer. And once again, if we were to naively pick likely winners and losers in the face of really widespread environmental change. When the going gets tough, it tends to be these smaller bodied organisms that have lower metabolic needs than large bodied organisms and tend to have larger population sizes, which increases their robustness in the face of mass extinction threats, as well as shorter generation times and therefore the capacity to rebound from extinction events more quickly than large-bodied organisms.
We can look at more recent examples still, can't we?
Yeah, of course we can. We can head across the street to the Museum of Zoology and keep talking about all of this. Should we go?
Oh, and why have you brought me here, Daniel?
Well, hi, Bill. So we're back at the Zoology Museum now across the road from the Sedgwick Museum to see some more evidence for the Lilliput effect, this time illustrated nicely by birds. So what we're looking at here is the leg of a gigantic extinct bird. This is called a moa from New Zealand. And these animals would have stood between 2.5 and 3 meters tall. These giant flightless birds went extinct relatively recently, within the last 1,000 years after human arrival. And the fact that these very large-bodied animals tend to be those organisms at most risk of extinction is illustrated really nicely by this, the tallest bird to ever live in the history of life.
And you've shown us the tallest. I gather you can also show us the biggest there's ever been.
Yeah, exactly. So we actually have some representatives of the heaviest bird to ever live just around the corner. But en route, we can see some nice mammalian evidence for this propensity towards extinction for large things. We've got the skeleton of a living wombat here. There's these lovely charismatic mammals endemic to Australia, closely related to koalas. And this is a living one. Well, actually, this one's not living anymore, but this is the living species. And here we have an animal called Diprotodon, this extinct relative of koalas and wombats that also went extinct relatively recently, about 40,000 years ago. And you can see the difference. It's the large thing that was less likely to make it through intervals of strain. Now, if we continue over in this direction, we can see something really extraordinary, which is the largest bird egg to ever exist. And actually, it's not only the largest bird egg to ever exist, in fact, it's the largest egg of any animal to exist in the entire history of our planet. And this does indeed come from a bird. It comes from a bird that used to live in Madagascar called the elephant bird. And elephant birds also appear to have gone extinct roughly 1,000 years ago. The history of this specimen is actually pretty amazing because it actually happened to be discovered by David Attenborough himself. And we can wish him a happy 100th birthday. He just turned 100 the other day. But to give you a sense of what these elephant birds were actually like, we can have a look at their thigh bone. This is the femur of an elephant bird.
That's a serious thigh bone, isn't it?
This is a serious thigh bone indeed, and you can tell just how serious it is when we compare it to a thigh bone from another gigantic bird. This is an ostrich, of course, the largest living species of bird.
And
it's
pathetic by comparison, isn't it?
Yeah, I mean, nothing against ostriches, but I have to say this elephant bird is absolutely enormous, by far the heaviest bird species to ever live. And just like the situation with the moa, these elephant birds endemic to Madagascar were, unfortunately, if not destined for extinction, at much greater risk for extinction, simply given the fact that they are absolutely enormous, with all of the risks associated with that we discussed over in the Sedgwick Museum.
And this process is still happening today?
This process is still ongoing. We know from data generated by conservation scientists working with indigenous biologists that there's strong evidence for body size reductions in bird communities around the world today over the last 100 years or so. And that's driven both by the selective extinction of relatively large-bodied species in various bird communities, but also body size reductions among surviving species representatives within those groups. So those two mechanisms of body size reduction in these communities are probably the same sorts of mechanisms that drive these body size reductions that we observe in the fossil record across mass extinction events.
So what we see in the Lilliput effect means that the larger species have disappeared. We're left with smaller species. That's had immense consequences for the evolutionary past, but it's something that's happening now, and we are seeing the loss of large individuals and large species, and that'll have serious consequences unless we do something about it soon.
Absolutely. Yeah, large species are always going to be at significant risk.